have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon? Or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Tyson and Kaku are raising the red flag about a possible hazardous collision between these two celestial bodies, which could be a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. The intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets, adding layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacy of space mechanics. The three-body problem in space is about figuring out how three bodies like Pluto, Neptune, and the Sun move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms axial vibration and latitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is axial vibration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation, named after three scientists, von Zeipel, Loff, and Kazai, who studied how things move in space. This oscillation describes how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity, affecting their movements. In Pluto's case, VZK helps us understand why its path around the Sun is so unusual. Even though Pluto's path seems erratic, this oscillation helps keep it moving smoothly over long periods. All of these components help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or get thrown off course. The three-body problem assists in understanding how these paths change due to the gravitational interactions of space objects. Studying this helps us learn about Pluto, our solar system, and distant worlds. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic. Minor deviations in initial conditions can lead to significant differences over millions of years. However, the unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping chaos at bay. Recent computer tests have helped us understand how the big planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a special connection with Pluto, where for every 2 rounds Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady. However, Neptune isn't the only one helping. Jupiter's gravity also plays a big part in keeping Pluto's orbit safe and stable, with Saturn contributing as well. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for a very long time, potentially even billions of years. It's as if Neptune, Jupiter, and Saturn are all working together to make sure Pluto keeps moving safely in space without running into trouble. These phenomena are essential in the context of the universe for maintaining the order and predictability of celestial bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with talks about it possibly crashing into Neptune in the future, understanding its orbit is crucial, providing a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly change its long-term orbit. Using computer simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations employ complex mathematics to mimic how Pluto and other space objects, like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even minor adjustments can lead to significant differences in Pluto's trajectory. Back in the late 1980s, these simulations revealed something interesting about Pluto's path. Even with factors like axial and latitude libration keeping it steady, its orbit can still be quite wild and unpredictable. If you start with just a tiny difference in Pluto's initial position or velocity, its path can end up looking really different over many years. Yet, even amid this chaos, Pluto's orbit remains stable for an incredibly long time, suggesting that its journey around the Sun has a form of order to it despite appearing chaotic at first glance. Predicting cosmic events, especially those involving chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainty. While numerical simulations provide powerful tools to understand and anticipate the future paths of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or oversimplification can lead to vastly different outcomes, making precise predictions daunting. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic universe. While we've made significant strides in understanding space, Pluto's case illustrates how much about the universe still remains unknown. Understanding the gravitational influences of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune? Despite all the complex forces attempting to prevent such an event, Tyson provides a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Known for popularizing astronomy, Tyson views the reclassification of Pluto not as a demotion, but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of continuous learning and adaptation. Tyson sees the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The intrigue of these unknowns, according to Tyson, is what makes astronomy so captivating. He keenly understands how space events and discoveries shape public interest in astronomy, believing that events like Pluto's reclassification or its orbital peculiarities can engage the public's imagination and curiosity about the universe. Tyson, along with other scientists, warns the public about the potential danger of Pluto's randomized course. After years of studying Pluto, he has raised concerns that the three-body problem might actually pose a significant risk when it comes to a collision with Neptune, which he suggests is long overdue. He emphasizes that such a collision could completely alter the universe's balance and trigger catastrophic consequences, reaching all the way to Earth. If Pluto and Neptune were to collide, it would be a rare and catastrophic event in our solar system. The collision would release an immense amount of energy, likely shattering Pluto given its smaller size and icy composition. Debris from the collision could spread across the solar system, potentially creating hazards for other planets and their moons. The shock waves from such an event would also affect the gravitational balance of the outer planets, possibly leading to unpredictable consequences across the solar system. As we look deeper into the future, Tyson and Kaku remind us that while the likelihood of Pluto and Neptune colliding in the near future remains low, the unpredictability of space means that nothing is ever truly certain. The careful balance of gravitational forces that has prevented a catastrophic collision for millennia could be disrupted at any time. As humanity continues to study Pluto and its strange orbit, we gain deeper insights into the mechanics of our solar system. But the uncertainty surrounding Pluto's future reminds us of the delicate and chaotic nature of the universe. Whether or not Pluto collides with Neptune, the question invites us to ponder the ever-changing forces that govern our solar system. This revised version maintains the overall structure while improving clarity and flow. Let me know if you'd like further adjustments.